Okay, here's a classic example in implicit differentiation. We're looking at the Folium of Descartes, which in this case is x cubed plus y cubed equals 6xy. Sometimes you see this written with other constants, 3, 2, etc. In our case, it's 6. So step 1, or part 1, part A, I guess, we want to find y prime at 3, 3. Well, we have a picture of the folium here as well, and you can tell that this thing is not a function, and anytime something is not a function, we need to use implicit differentiation. We know it's not a function because it wouldn't pass the vertical line test. But looking at that picture, if you had to guess the derivative at 3, 3, what do you think it would be? Right, we can imagine a little tangent line in here, maybe like that. And I'm thinking that line would be a perfect diagonal, so the slope would be -1. Now, I'm not sure if that's what it is. I just have a hunch that's what it would be. I also have a hunch that at 0, 0, we're going to have problems, right? Because this thing loops around upon itself, so I can't imagine how we would do the tangent line at 0, 0. Would it be this one? Would it be this one? You know, we have two things going on at once. So something tells me we're going to have a hard time for part B, where we are asked to find y prime at 0, 0. But let's start with part A. Find y prime at 3, 3. Okay, we'll use implicit differentiation here. So let's take d by dx of both sides, d dx of x cubed plus y cubed equals d by dx of 6xy. Now we're taking y to be some function of x, so y equals y of x. So every time we take the derivative of across y, we need to apply the chain rule and write an extra y prime in there. So that's the one thing you need to remember for implicit differentiation. The shortcut method, since this dx down below doesn't match the y, we need to add a y prime every time we take the derivative across a y. Again, it all stems from the chain rule. Okay, let's do it. So we have 3x squared plus 3y squared y prime. Okay, well, just in case there's any confusion about where this y prime came from, we had essentially y of x cubed prime. So by the chain rule, we would have 3y of x squared, and then times the derivative of the inside times y prime of x. So we're just applying the chain rule. It just doesn't look quite as convoluted as this because we're keeping things very crisp as just y's, but that's what's going on behind the scenes. Okay, equals, and then we have the product rule, so I'm going to call 6x my a term and y my b term. And then the product rule is a prime b plus b prime a. So here we go. Taking the product rule here, we have a prime, so 6. B is just y, plus b prime a. Well, b prime is y prime, right? Because it would just be derivative of y would be 1, but then we have to tack on the y prime. Or you can just think of it as the derivative of y is y prime. Okay, times a, 6x. And if you really don't want to think too hard about it, a very pragmatic approach, this is the derivative with respect to x. Y does not match x, so we tack on the y prime when we take the derivative. Okay, it's all algebra from here on out. We need to get this y prime by itself, so I'll get everything with y prime in it on one side of the equation. 3y squared y prime minus 6xy prime, and everything else on the other side. So we now have 6y minus 3x squared. We factor out a y prime now, and they all kind of work the same way, the same steps. You get the y prime stuff on one side, you factor out a y prime, you divide everything else away. So factoring out a y prime gives us 3y squared minus 6x left behind equals 6y minus 3x squared. And now I will divide out by all the stuff attached to the y prime. So in this case, 3y squared minus 6x. Divide by that, giving us a final expression for y prime. Y prime equals 6y minus 3x squared all over 3y squared minus 6x. So there's our derivative. We want to evaluate this at the point 3, 3. So that vertical line there is a way of stating that. Well, plugging in for 3 for x and y gives us, let's see, 6 times 3 is 18 minus, how about 27 over 3y squared would be 27 minus 18. Indeed, -1, as we expected. Now, I would argue you couldn't solve this for y. Even if you wanted to not use implicit differentiation, and you're like, no, I'm just going to solve for y first. Go ahead and try. Try to solve this equation for y so you have only y on one side and everything else with x's only in the other side. Right? If you can do that, great. Feel free to not use implicit differentiation. But I don't think you can. And actually, you have to use implicit differentiation anyway, because that's what we're setting out to use here. Okay, let's try part B. We already expect this to be a strange derivative, but we already have our derivative, right? We'll take the same derivative and we'll plug in 0, 0. So now we're simply evaluating y prime at the point 0, 0. And you can see from plugging in 0, 0 here, we would get 0 over 0, which is an indeterminate form. So I'll just write undetermined for that derivative. You could write indeterminate, you could write undefined. You wouldn't want to say infinity, and you definitely wouldn't want to say 0 or infinity, really. It is undetermined. We can't say 0 over 0 is nonsense mathematically. We can't say anything about it, so which makes sense. Visually, we can't talk about a derivative when two lines cross right there. So that's pretty much what we expected.